C, and assembly and C are basically one-to-one, so this is almost relatable. But assembly is a function in C that just prints something to the screen. And you can use it like printf, just a string, like I am 10 years old, would have worked here. However, you can also have use it to format stuff. So you, for example, this line would mean print this, and this means and print this, and this means and then the next thing will be a string. So it's basically saying print the next string, and the next string being I am 10 years old. So then, to move on from this program into assembly code, we first want to load the first register into the first argument, as per se. And as I just showed you in that OneNote thing, the first argument will be RDI. So we say move the format string, which I have here defined in text with ASCII Z. I will get back to that later, to be the string %s into RDI. Then we want to have the second string, which is
why is it RDI?
In the calling convention, which is also findable in the. Give me a sec. I want to check that I'm not dying in RuneScape. Okay, no.
It just is.
Yeah, the calling convention is basically some rules made by the people from. By just the people who designed the infrastructure, like the C library that we're using. That the order that you will give your argument in is RDI, RSI, RDX, RCX, etc.
And from what I can find, you 0 RAX because that is also used somewhere for.
I think
vector registers used. I have no clue what the fuck that.
Yeah. I saw it somewhere as well about it being a vector register. I have no clue what the fuck it is. It might be that if it's 0, that it expects stuff from.
You need to 0 it. Printf does something with it. If it's 0, it's fine.
Yeah, but the weird thing is I've used it later. I'm gonna explain this, and I'm gonna do a little test to see if my suspicion is correct. But yeah, we're gonna have the first.
Excuse me. Why do you have to use the %s? I'm confused by that. Can't you just print the string directly?
You could, it will work, but I was testing with formal strings. So I did like, at a certain point, I did like %s%, I think, x. That's like print a hexadecimal number. And then I could have this command in the end, namely, and then 0x42, for example. Then it would print I am 10 years old, space 42. But yeah, I just did that as an intermediate step to see if it will work, and it did. Oh my god, I cannot type. So yeah, I moved the first argument, which is %s, which is in here, into the RDI, and then the second argument, namely my string, into RSI, and then I call printf. Now the way I define these arguments is basically the way that that the computer knows where a string stops.
Mic off.
Is it has a 0 byte afterwards. So basically, come in.
In the chat, there's a link which goes to my Twitch, which has a stream link for the people who can't see the stream.
Oh yeah, my brother is live streaming me to Twitch, and it's on there as well. I guess we can make a VOD. Okay, so basically, what my string is it's a location in memory where the binary values for the characters of the string. So the binary value of I is like, I don't know, 0x or 0b 1011100001, whatever. Next one is 10, whatever the fuck. And then it goes on and prints all of these characters, including \n, which is new line, into that string. And that would just be it if it was .ASCII. However, it is ASCII Z. And the difference between ASCII and ASCII Z is that there's a 0 bytes after it. And a 0 byte is basically just a byte with 8 zeros in it. So just 0, 0, 0, 0, 0, 0, whatever. The way the computer knows that the string stops, if it keeps looking for characters, so like I space, A, M space, 1, 0 space, etc., until the byte is 0. And the moment the byte is 0, it stops reading and it knows, okay, I'm done. That way you don't have to specify to the computer how many bytes it is. Hell, if, it will store this in this part of memory that we are now conveniently calling myString, and then format string, which is like the %s, is also pointed directly behind that in memory, and then you've got all the code in main. So like when we compile this, it will literally in the memory of the computer store all of this just in a row like it is here. And we can actually prove that, because if we remove the 0 byte behind this I am 10 years old, it will keep on reading until it finds the very next 0 byte, which theoretically should be after format string. I already mentioned before that with /compile.sh, it compiles in.s to go to out. So now if I should run out, yeah, it reads the I am 10 years old, the enter character, and then the very next thing in memory is the %s string, and then it finds a 0 byte, because this thing still is ASCII 0. So let me change that back, and now it should, after compiling, just run I am 10 years old. Now there's this.
And if you put both of them as key, will it just crash?
I don't know what it's
That is actually a good one. We don't know what is in memory, but it will keep reading until the very next 0 byte. And I did this before because somebody in the other server, there's like another server with like all years of computer science and engineering, and there's like people from other years as well, and they helped me with this. But it will show a part of the code as ASCII. So here it says 2 H's, and those H's are actually the instructions that come from the move, but then in the binary font. So let me see if I can get this more
semi-consistent. Because we're gonna add a
So assembly files are sh, right? .sh.
No, the assembly files are .s, but .sh is a bash script, which is basically the language that Linux uses, that I've made to compile my in.s into out. So whenever I do, whenever I change in.s, I cannot directly see the output in out. I first have to compile it using /compile.
Oh, so you compile it to the bash and then you run it. Okay.
Yeah, I compile it from assembly into a binary file, an executable file, and then that gets run with /out. And / just means run this file in this folder. So now if I get everything back again, I have ASCII 0 with a 0 byte behind it. And then of course I have to compile it, and then again do out, and it will just print that.
Can I add a few side notes? For the zeroing RAX, from what I could find about vector registers, they are a type of register used for very large instructions or operations or math on larger data pieces. So these are 256 bits.
Can you open the source code again? I just want to copy.
That's...
I will put all the things, so like the source code for all the files I'm going to be showing, in the Discord afterwards.
Mic on.
And as for registers, make
Mic
sure
off.
you use the ones that are in the convention. Because assembly itself will use, or your computer itself will use, some of the registers during operations. So the ones that are set in convention are generally safe to use, as they are only used if you as a user dictate so. Sometimes some registers are used in between operations, and if you are not aware of that, and you try to take your variable out, you basically have a random number generator.
Yes and no. If you call other functions while stuff is in those variables, then that can happen, yeah. But in most cases it will not. I will now...
Depends completely on the registry.
Yeah, okay, there are some registers like you cannot expect the instruction pointer to stay the same.
Some of them are used for the weirdest things or in the background.
Yeah,
You're not even aware of it, or it is used for random things, and the computer just throws in different things.
Yeah, but 99% of the cases, especially with the more common registers like RAX, RBX, RCX, RDX, RSI, RDI,
those
etc.
are totally safe.
That will not change.
But I've already seen random number generators last year, and it is confusing as hell because you have no clue where your error comes from, and every single time it's a different error.
About that, now we will get on to the next part, which is debugging. There's this command called GDB, and actually I am using a variation on GDB called pwn debug, which is just a version that pen testers or hackers use, and it's like way better than the normal boot GDB, and I will show you why. But basically, I can say GDB out, which is the GNU debugger, and then with the file out, it'll load everything in, and then I can say start. And by doing start, let me make this or can I scroll in this? I can scroll in this proper. So by saying start, it will walk through the program, and here you can like literally see where it is in your program, and it will show what it's doing. So here you can literally look at the registers as they are written. So indeed, here you can see RCX and RDX still have other stuff from other functions, but as soon as you write 0 in it, you know, it's 0. So at the beginning, if you're ever going to use a register, always make sure to start out with just putting 0 in it.
Or move something into it.
Yeah, move something. Like here I'm moving the address of my format string into it. That's okay too. But yeah, here I can just say, okay, next instruction. And now you can see it has moved 0 into REX. It even shows a star to show like, hey, this register was edited from the last time you were active. Jelle, if you can hear me, can you send a message to my girlfriend that I'm busy and I will not be replying for a few minutes?
Mic on.
Thank you. So we can see. Thank you. The next instruction, move
Mic off.
formal string into RDI. This might look really weird, but this disassembly actually uses the Intel syntax. So yeah, instead of move REX into 0, this means move 0 into REX. However, the source code file is always correct. So if you're worried about like, hey, is it in the right way? You can look here. So you can see this will move the address of my format string into the RDI register for my printf to read. And I can look at which was it, RDI? I can look at RDI and see here it's loaded with 1. Then I can say go do the next instruction, and I can see now the address of my format string is now loaded into RDI. Then in the next one it will move RSI into the value of, or the address of my string into RSI, and my string is the I am 10 years old. So I can say next instruction, and it will do that. So here you can see RSI as my format, RDI as my format string, RSI as my string. And then the next instruction will be a call to printf, which will print out I am 10 years old using that, using the format string and my string. So now I should here in the top see I am 10 years old. And then if I do the next few lines, it's just all gonna be like garbage that the compiler put around my program to make sure everything works fine. But continue. But yeah, everything after the main here you can practically ignore because that's not that's done by the library itself. So this was the most basic program I can think of. You can actually with Ctrl D. The most.
Yo, who the fuck is that loud Discord noise?
I have no clue.
It is literally burning my ears.
I have a question from my brother. He says, are RSI and RDI just storage registers? The answer is everything is a storage register if you try hard enough. However, I would very, very, very much advise you not to use RBP, RSP, and RIP as your storage registers, because that will fuck shit up.
In the lab manual are ones that are used as convention. Use the registers that are given there as convention for storage, and if you run out of registers for storage and you would need more, which will not be often until you get into the bonus assignments, use the stack.
Yeah. I've got some other programs here, so let's see, Untitled Assembly.
And I'm gonna give this little side note for you, because at the start you said it's basically C. Okay, who the fuck? You basically said it's the same as C. This is with the C library.
Yeah.
Printf like this normally doesn't work like this.
Yeah. Base Bear assembly only has the system calls like
yes,
right.
syscall, and you have to actually announce how many characters are in the string.
Yeah. Fortunately, we do not have to deal with that because the command we use to compile it, as you can see in vi compile.sh, is gcc, and that is the GNU collection compiler collection. I'm dumb. And that basically bundles all the right files, all the right objects, everything that you need, C libraries, etc. It just loads it into there, so you don't need to worry about it. And since this is the command we're going to be using all the way throughout the year, you can just use library functions like C functions if you want to.
Bonus assignments.
Yeah. However, there is indeed a bonus assignment where it says make printf, don't use libc. You cannot just say
I already made it.
scanf printf. Okay, it works.
Wait,
Okay. Sorry, what is the difference between, for let's say, for example, EAX and RAX? Like, what's the difference between the E and the R at the beginning?
Okay, so the difference between that, and let me see if I can pull up the image. Jelle, if you have the image in your OneNote, please send it to me. Yeah, I'll go to the lab manual because I assume I'll be doing it more. I'll be showing more stuff.
Because I know E is for extended, but what does the R stand for?
The actually, there we go. Jelle showed me the picture. Let me see if I can get it on the screen real quick. Okay, so this is the version of how it is. Yeah, how do I say this? So we got all these registers: RAX, EAX, AX, AH, and AL, and they basically all point to the same space in memory, but then at like different, different locations in the space. So I will now proceed to draw a nice paint diagram.
Great.
Which is always the best solution. Imagine we have this number in here. My paint skills are absolutely extraordinary. 1100. This probably isn't 64 bits, let me tell you that. So when you've got RAX, you've got all the 64 bits that are in there. Then when you've got EAX, it will only use the last 32 bits of this. Usually, you just don't want to look at all this and you just want to use RAX for everything. However, there will be some instances where you use like the lower bit registers, and I will be going through that in a bit because I have made a kind of like a capture a flag type program for other people to disassemble, but it's like a great example of how everything works. But basically, if you write like...
I understand, thank you. You're a legend, by the way, thanks.
Thank you.
Mic on.
I don't know who's asking, but can you please just put it in the chat because I can't understand anything.
Yeah.
Yeah, your mic shit. I'm sorry. But yeah, basically, if you put like a value of 64 bits into RAX and you read EAX, it will only read the last 32 bits. If you want the third byte out of RAX, you can just use AL plus 16. The third byte out of RAX, you can just use AL plus 16. No? What the fuck is wrong with you? No. RAX and it's not just a location in memory. You cannot just change shit with that. However, Jelle does make a good point. That is something I still want to show, and that might help with visualizing how memory itself works. But yeah, basically these are just like the sizes of the registers, and you practically only use this if you, for example, only want to have 8 bits to work with. Jelle did mention a great point. He mentioned that, wait, copy, I already moved it back, so let me get it out real quick again. My Hello World example. So here we've got the ASCII thing, I am 10 years old. Now it is very important to understand that this is all just bytes written into memory. I is a byte, space is a byte, A is a byte, M is a byte, etc. Now we've got this here, and the syntax that you're seeing here is this is a label. And this label basically means this is the memory address at which format string or my string or whatever is located. And the fun fact about that is basically this is just a number which is like a location in memory where my string resides. So for example, if I say add, and now I'm going to grab the lab manual real quick because I am good but not that good that I don't need a lab manual anymore. By the way, you can find the lab manual at the CO course, and then content, and then scroll down to let me see, the table of contents, I think. I used to look it up somewhere else, but let me see where it is now. I think I can just look for lab, and then it will show the lab manual. There we go. If you look for lab in the top left here, it will say the lab manual. This thing is a fucking lifesaver. We are using AT&T syntax. Nobody uses AT&T syntax anymore. Everything you'll find online is on Intel, so this is practically your only real, like, your own real source of information. So everything you will need will be in here mostly. If you have more questions, just hit me up.
It's the same as last year.
Yeah,
it's
still useless.
No, it's very useful. It has everything.
No. Like this thing is very useful. It's the most useful thing ever. But AT&T syntax still useless.
You have no fucking clue what you're looking at.
Exactly. So here we've got the add instruction, namely add source destination will be destination is destination plus source. So if I want to take the RSI or RDI register, I can say add 8, and then because it's a number, this is important, because it's a number, you gotta add a $sign in front of it. That is the general terminology. A $sign in front of something means it's a number. A % sign in front of something means it's a register. And yeah, people, you can all ask me, but preferably also other stuff if you need help. There was a link sent to the CSE Discord, like the more general CSE Discord. They have a special assembly channel in the year 1 list where you can ask questions like this. I'm going to be in there almost all day trying to answer questions. But you can also just ping me or send me a DM, but the best thing is to go to that channel because there's also a ton of other smart people in that server that can help you.
There's some big brain people in here, holy shit.
Could you please explain quick maths? Like, very easy, just additions?
Well, actually, you got 2 plus 2, that's 4, minus 1, that's 3. Anyway,
exactly.
No, but here we've got my first math instruction here, and that is add 8 to RDI. So to understand what this does is first you're going to realize that move format string into RDI does nothing else than moving the location in memory, so the number in memory where format string is located, into the RDI register. Then we take the number that is in RDI, namely the memory location of the register, and we add 8 to that. Or let's add 1. We'll add 1 to that.
That's gonna fuck it up.
You might think, however, you guys can see my pointer, right? The white underline.
Mm-hmm.
Yeah.
Okay.
Yeah.
So formats or my string will actually point to this location. If we add 1 to it, all it's going to do is move it here. So it's just going to print I'm 10 years old. I messed up here because I'm incrementing the format string, but I actually wanted to increment my string. So here we go. And now if we compile this with /compile.sh, we can see a number of operands mismatch for add. Don't leave spare code hanging. Now it compiles, and then we can and then we can do /out. And it should now only print space I'm 10 years old. And there we go. Can somebody put the link to the server in the chat? I think it was somewhere like.
Oh, fucking god.
Hmm? Actually, I might see if I can create one real quick for you guys.
I have a link in CC General.
I'll do the link.
It's already
Continue
in
with your
CC
stuff.
General.
Okay, cool. So we can actually look at what this is doing by doing, again, GDB out, doing start, and we can look at the register. So if I say next instruction, next instruction, next instruction. So here we've got RSI pointing to the location in memory, namely 0x401122, and here it's going to add 1 to that. 1122. And here it's going to add 1 to that. Somebody, you're echoing a fuck ton. Please stop. Thank you. I can see the admin's already served muting people.
Yep, so we're muted, no worries.
Okay, so now if I do next instruction, what should happen is RSI should be incremented by 1. And as you can see, RSI is now 0x401123. And there's actually this instruction in GDB that allows you to look at memory while it's running. So I can say, show me the memory, and this syntax you gotta just look it up. But show me 10 SB, yeah. So 10 strings, and then the B means in sets of bytes at 0x401122, and here it prints the I am 10 years old /n. That's the first string it finds at that address, and then it goes on to the next one, namely %s or other stuff.
Random shit.
Yeah, this is literally like the code it is trying to read. Okay, but now if I start at 2.3, it'll see like, hey, it will actually see for itself that it is 1 character past the start of my string, but it will show here that I'm 10 years old /n. And if you want to look at it like binary, you can change it to an X, and you can see like, okay, these are the bytes that are literally like, that will change to the string I am 10 years old. So this is a space, this is a space, I recognize those characters. But yeah, so you can look at memory while it is running, which is really, really important for debugging. Okay, that was most of it on just the Hello World program. There is another program that I've written, which is scanf printf. So that is copy assembly / For some reason, I spent like a lot of time yesterday doing all of this, and I didn't know I would be doing this today, but I've got like everything I need. So we've got the program scanf. It's now called in.s, but it's like scanf printf. And it's got a bunch of stuff that I don't need. I'm going to remove that real quick. Yeah, and the way to... Okay, so the way to remember, or how I remember the order of operands, is move buffer into RSI. Okay, so there was this thing about function prologue and function epilogue that the guy said in the slides, and it's basically preparing the stack so that you can use it for yourself and it doesn't interfere with stuff used outside of it. You can do that with the enter function. And in this case, I say enter 0x10, 0, which basically means enter gives me 10 bytes of space on the stack, or 0x10, which is 16 bytes of space on the stack to work with. And 0 just means the default form. So this is just a shortcut for saying move RBP, RSP, push RSP, sub RBP 10, whatever the fuck that bullshit is. I don't care. enter works. So here we've got two functions. We've got the function scanf format buffer, and that is it. And then when you look at like the format and the buffer, you can see that scanf, the format is a string, so this basically means scan a string, and the buffer is not yet defined. So what this means is, first of all, scanf is a way that you can, or a function you can use to scan or to like read user input in C. And basically, what this does, also if I say anything wrong about C, correct me, I have never programmed a C before. This is all just a function. But basically, it means scan a string that the user is inputting, and that just means until you press enter, and put it at the memory location buffer. And as you can see, buffer here is skip 30, which basically means leave 30 bytes empty because I am going to be using this. So after this, when I enter something, it's going to move that into the buffer, so into the text here, or into the data segment here. And then after that, I move the location of buffer back into RSI, and the format is again a string. And then this is just the good old print a string, namely buffer. And the buffer will point to the location where I've stored my Jana is asking in the chat 30 hexadecimal. This is a decimal number. If I wanted it to be hexadecimal, oh shit, I should write 0x in front of it. That goes true for everything. If you're not writing anything in front of it, it is a decimal number. If you write 0x in front of it, it is a hexadecimal number. Please say I in the chat if you do not know what a hexadecimal number is. Hey, I mean, most people know, but there's this one person who, there are multiple people who don't know what hexadecimal is. Okay, I'm gonna grab out the trusty notepad. New file. Let me see if I can zoom in a bit. So our numbers go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then they go 10. This is a 10-based system. Then we've also got 0 base, which counts like this. 0, 1, 10, 11, 100, 101, 110, 111. So this is binary. But then we also got hexadecimal. And hexadecimal is, instead of a 10 or a 2-base system, it is a 16-base system. So it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E, F. And then it goes to 10, 11, 12, 13, etc. However, in decimal, which is the system that you're used to, this is I cannot type. Jesus Christ. So here you can see kind of how it works. So 0xf would be the same as decimal 15, and 0x10 would be the decimal 16. And computers calculate a lot using binary, but to make it more readable for us humans, they usually print stuff out, or the disassemblers usually print stuff out in hexadecimal. And the thing about hexadecimal is it's really good at working with binary numbers. So a binary number can go from 0, 0, a byte in this case can go from 0, 0, 0, 0, 0, 0, 0, which is 8 1 0 zeros, to 1 1 1 1 1 1 1 1, which is 8 ones, and that is in decimal. The first number is 0, and the second number is 255. So a byte can range anywhere from 0 to 255. Now the way this is turned into hexadecimal, and shown as hexadecimal, is you've got the first 4 bytes. This is 0 to 16, and this is also 0 to 16, which is great because hexadecimal has 16 things. So 11111, that is 15, so that's F, and 1111 is F, so 0xFF is 255 is 0B, and that means binary numbers, 11111111, and yeah, so that's basically how the computer shows it. Now I said just now, here you can see the you can see the bytes that are used to express the string. So here you have, for example, the byte 0x20. Now in binary it would be, or in hexadecimal it would be 20 is 2 times 16 plus 0 times 1 is 32. So the binary number 0x20 is the decimal number 32. And it would be the binary number 0b 00100000. But yeah, that's the crash course to hexadecimal, and that's basically all you need to know is it counts until 16. 0x10, that is 16, and 0xFF is 255. That's basically all you need to know. Back to the program. Let me see, what was I doing again? Okay, so first let me see if this function works. Compile out a, yeah, prints A again. So I believe 1 should be the position, the 1 should be 1 position to the right if I counted correctly. As in this one. Well, let me see, we've got this number which is 0 and this number which is 2. So 0x2, 0. So this is correct. But thanks for keeping me sharp. Anyways, so now we've got this program, which, as I said, reads a string into the memory area buffer, and then prints set string out to the screen using printf again. So then I was like, okay, if you do out and you type a bunch of A's or like A, B, 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 it will just print the same thing out to the terminal. That's the purpose of this program. Now, if we look at this in GDB, we can see this. Happening. So if we do disassemble main, this is the program in assembly, but then that is like what is reconstructed from the binary. So here you can see the 2 memory locations and everything. I prefer, yeah, this is being recorded in a Twitch VOD. I prefer seeing it like this. So I'll walk through the instructions real quick. And now it's doing the call. A, B, 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 B. Now the thing is why people in programming often use A's is that is the binary 0x41, which is often used as something you can recognize real quickly. So for example here, I print, I say print 30 hexadecimal bytes, or hexadecimal bytes, at the location of the buffer, which is 0x404038, which I can see right here. If I do this, it should print what is currently being stored in the buffer. And in this case, that is 4141414142424242. Apparently another 42. Did I probably inputted 5 B's instead of 4. But yeah, so now we know at our buffer location, it should it has stored 4 A's, 5 B's, and then a bunch of zeros. Though for string f, all those zeros won't matter because at the very first 0 it'll say, okay, my string stops here, I am done with this. And now if we do continue, it should print that out again because it the same as first thing, printf the string buffer should just do that. Now we've got a more interesting program. Spoilers for the CTF that I made. So if you want to do this yourself and already have quite a good understanding of assembly, I will send the binary file your way, and you can try it out. But I think it's worth to go over this because this is like my most quote-unquote complicated program yet. In in .s. So basically what we have here is we have a file, compile, out. It asks for a password, and if you enter something wrong, it is wrong. And the purpose of this file is to find out what the password is supposed to be. Now, if we look at the in file, it is not just a simple compare one string to the other, so that's why it is worth to like go over this one by one. So let's look at the program. First, we've got something entering the function prologue, giving me 16 bytes of space on the stack in case I wanted to do something with the stack. I don't think I did in this program, but I just wanted to have it just to be sure. I make a few declarations about memory in the beginning before the string, so let's go over that first. We've got buffer, which is a 30-byte buffer where I can store my stuff, which is being hosted in .data. And this is the first time I'm mentioning the .data, .text things. As far as I know, the difference between these is that .data has writable space where .text can only be read from. So here I've got like a key, some few strings. This cannot be changed.
Sorry, quick question.
Yep.
Why would you compile this with NoPy if it's a CTF? Doesn't that kind of ruin the...
Oh yeah, it does. But it's like not a advanced level CTF. Anybody who's relatively good at CTFing can do a GDB disassemble and look at the code and figure it out within 10 seconds. But like,
okay, great.
I wanted to give it to people who never did assembly before, so I wanted to. I even gave the assembly file to another group, and they still had a little bit of problem figuring it out. But that's why I'm going through it here now.
Okay, nice. Thanks.
So we've got the data area, which is writable, and that's where we keep our buffer, so we can write to that. Another thing, if we move this, so let me see, 2dd space, if we move this and we compile it and we run it, it will give a segmentation fault. Now, segmentation fault is one of the errors that will occur very, very often in your journey on writing assembly. And it basically means fuck you. That's it. So it is something that is wrong with either memory or registers, and something is wrong, and good luck on figuring it out. Your best bet is running through it with GDB, seeing on which instruction it crashes, and then trying to figure out what it does, why it doesn't work. But yeah, it doesn't give it like on a platter like Python saying, actually this is a type error, you should be using a string here instead of a character array. No, fuck you, segmentation fault. Anyways, back to our regularly scheduled program. So I've moved the buffer back into the writable data space, and text still in the read-only data memory. To answer the question from Julian, you can skip assembly altogether. However, that is one of the 3 things that you cannot that you can fail. I wouldn't risk it. Assembly is bad, but it's really not too bad once you get the hang of it. And that's the point. So now if I compile it and do out again, yeah, it works. So to go through my thing, I here enter the function, allocate 0810 bytes of memory, which is 16. Then I print the message from my string, namely, please print the password, which I do by moving it into the first argument, calling printf. So this is basically, like you guys said, printf, please enter the password. So I'm skipping the %s again, because at that point I realized, wait, I can just skip that. That is a lot shorter code. Then we do call scanf, and here is the command scanf a string into the buffer location. And theoretically, if you're writing C code, it should be a dereference because you're passing the pointer, blah, 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 blah. But basically, we are just like the previous file, writing whatever we read from standard input, so basically what you type, into the buffer. Then we move the buffer, or the memory location of the buffer, into RDI and call strlen. Now you guys haven't seen this function before, and what strlen does is it takes the buffer, or the whatever string you want to check, and returns the length of it, and basically just goes on until it sees a 0 byte and it knows, okay, I'm done. So strlen returns into RAX. So after this function, RAX will contain the length of whatever we input. That is another convention, by the way. If you write a function, the convention is to leave your output into RAX, which is something you should watch out for. So if you're calling a function, make sure whatever is in RAX is stored somewhere else safely, either like pushed on the stack or something. Okay, now I will check if RAX is equal to 9, and if not, I will jump to fail. Now I've got a few labels here, and just like you can use this, like these labels as like the locations in memory. So like key will be the location where all these bytes are. My string is the location where my string is. You can also have locations like loop, and loop will start at this very byte, and that's basically where it will resume execution if you jump there. So basically, a jump is nothing more than remove the instruction pointer, so what is currently executing, to this place. And in this case, it will say jump to fail, so we will skip all of this, go to fail, and say, okay, print the incorrect message and leave. Guys, can you please keep everything on subject? Why jump not equal instead of jump? Well, we want to see if our input is 8 bits. And here I say 0x9, but that's actually the same as just saying 9. It doesn't really matter because it's only one character. And if it's like 0 to 9, then it doesn't matter if that's just decimal or hexadecimal. But I am checking, is the length, which we got from strlen, the same as 0x9? And if it is not equal to 9, we'll jump to fail and it will print the exit message and leave.
Also, is there a way to avoid spaghetti code with those jumps and stuff?
No. Basically, the only way to...
Only like go to?
Yeah. The only two things you can do is like go to, or like the jump, which is basically the go to, or you can define functions, which you can, for example, do here and then say call and return, which will handle it properly so that you can go back to that. But this is not a situation where we would use that. So here it's going to get a little bit tricky, and this is basically the implementation of a while loop or for loop. Basically, for loops are glorified while loops. That might sound really weird, but that's the way it is. So basically what I'm saying here is we start with REX is 0. Then I check is REX 9. If it is, that means we haven't broken out yet. So basically the code here is I'll write it here while REX is less than 9, and then the code and then run code. So basically what we do is REX starts at 0, and then at the end it increments it with by 1, saying here inc loop inc REX, and then it jumps back to loop, so it jumps back to here. So and then here it says REX plus plus. So this is basically just a for loop that runs through the bytes 0 through 8, not including 9. Yeah, that's increment REX. This is just like a general overview of the entire loop block.
So the CMP code, does it compare like equality or the because
that's the fun thing. CMP compares everything. So what it does.
How do you know the result?
That's by what do you do with the jump instruction. So basically what you do is you say compare 9 to REX, and that will set a bunch of flags. If it's greater than, it will set a certain flag, and flags are just like registers. They're like tiny spaces in the CPU's memory that will that they use to keep track of it. You basically do not need to worry about flags. all you need to know is when you compare two things with CMP, you can use the different jump commands. And let me see if I can get the table with the jump commands here. You can use the different jump commands to see what the result was of that comparison. So if you say GE, it will check if these two are equal, which I am here checking. So if it is equal, jump the label correct. You can say jump not equal, GNE, to say, okay, if not correct, jump to fail. You can say GE, like greater than or equal to, then you see if something's greater than or equal to or whatever. It goes on.
Okay, thank you.
You're welcome. So now, I am actually using the registers of the lowest bytes, so the ones we talked about just now. What I am doing here is I move the memory location of the buffer into R9 and the memory location of the key into R8. And this here is a special kind of operand, the brackets operand. So if we go to the lab manual, it will say in the lab manual here, the accessing memory with displacement base index scale. And that will basically mean, in this case, I've got 0 for displacement, the buffer as the main memory address, RAX as the index, and scale is 1. So if I am to draw that out, imagine buffer starts here. Then if we have, let me get it again, it's buffer RAX 1. So when RAX is 0, it will be buffer, so this location of memory, plus 0 times 1. Then it will stop. And this is like bits, but I'm gonna just say that these are bytes to make it more clear. So if we have RAX being 1, it will start at the base, which is buffer, plus 1. So then it will look at this byte. And if RAX is 2, it will look at this byte. If RAX is equal to 3, it will look at this byte. So it will create an address that is equal to the base plus RAX times I. Cancel. So that's what we're doing here. So we take the buffer itself, so the address of the buffer, I mean, and we add RAX plus 1 to it, which will generate a memory address of the buffer or something further. And then we use mov-b, which is weird. You guys haven't seen mov-b before. Basically, it is R9 plus RAX times 1. Yeah.
Mic off.
Okay. So we are using mov-b here, and if you look at the lab manual, you can actually see that the instruction set doesn't say anything about mov. It just says mov dot. And the dot in this case can be used to specify the size of what you're moving. You're almost always going to be moving keywords, which are 64 bits, so you can almost always ignore this. However, in this specific case, you cannot. So mov-b will only move 1 byte into a register. And here I am using the BL and CL registers, which, as you can see here, are just the last 8 bits. So I'm really only looking at the last 8 bits of the register, B and C, and that gives me a memory area of only 1 byte to work with. Okay, so now what I am doing is I am moving let me see. I am moving the character at this location into BL. So if I have, let me just erase this all. White. Okay, so if I have, for example, my input is password, by mov-w, I will say, for example, this is the base, like it starts here, and there's a bunch of data in front of this, but we don't care about that. When RX is 0, it will move this character, this byte, into BX. Into BX. That's, oh my god, it's fucking, terrible. Oh no, that's too big. But yeah, basically B is in BX. And I also have the key. So I'm looking at buffer and I'm looking at key here. As you can see here, the key is just a list of bytes. And these are just just values that I very carefully handpicked just to fit this, whatever we need to do with this. So, we are doing mov_b the buffer into BL, and mov_b the key into CL. And this is basically just saying, in, for example, Python code, it would be BL is key REX, and CL is buffer REX. Yeah, basically what it's doing.
Mic off.
So, and you can already kind of get an image of what is going in your head is what's going on. So we've got the first, when it is the first character, it will load the first character into BL and CL. Then we've got, it's the other way around, is it not? Oh yeah, it could very well be. Let's see, R8 is used for CL, R8 is key. So yeah, my bad, this is key, and this is buffer. So this is what is being done by these 4 lines. Then we've got an XOR command. And the XOR, we basically XOR 0x69 by BL. Does anyone not know what XOR is? And especially in the binary sense. So you might have had it in, alright, there's already a few people. So basically, if I open Python, let me see if I can enlarge this a bit more. No, I'm just going to do it in Notepad then, because I cannot enlarge it. So basically, imagine we have 2 numbers. Namely, the binary numbers 0, 0, 0, 0, 0, 0, or 0, I'll just enter a number, and yeah, this. So when you XOR these, basically what you're doing is for each and every bit, you're doing an exclusive OR. So you're saying, okay, and for the people who forgot it, exclusive OR means it's off if either neither or both are true, and it's on if only one of them are true. So exclusively one or the other. So here we see only one is true, both are true, so that's false. It's neither are true, so that's false. One is true, 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 one is true. So this will be the output of these numbers XORed. Hey, shut up about my acacia trapdoor.json. So this will be the XOR of these 2 numbers. And the beautiful thing about XOR is if you XOR something with another thing twice, you get it back. So the command, the character for XOR is the caret, or like the roof, as we call it in the Dutch. So, but here is basically how it works. Or A square caret C is B. So you're basically creating your own kind of like encryption, but it is completely reversible. So basically, if you say I XOR something, I XOR A with B, and then I XOR that with A again, or with that with B again, you get A, or with A again, you get B. It's basically a reversible encoding. I'm very bad at explaining this, so I'm sorry, but I'm going to continue.
It was fine, thank you.
All right, that's good. So here we take a byte of the key. So for example, 0x2a and 0x69 in this case, and we XOR that. So let me look at what that is in Python. 0x, was it 2a? Was it 2a?
Yeah, it was.
Yeah, 2a. Cool. Into XOR 0x69 and wrap that around a nice little hex to see what it is. So that is 0x43. So in some way, we want to get 0x43 as the first character in the password. Now luckily Python has a neat little feature called character, where you can just enter the character and see what comes out of it. So the first character should be a C. Yeah, okay. I confused my own password. So, it now will check if, where it is? Yeah, it will now check if the first character is XORed with the key, if that is, in this case, a C, and if that is correct to the first character of what we have entered. If that is not true, that means it's already failed and it'll jump to fail, print wrong, and quit. If that is true, it will do nothing. It will go on. It will go to the next character. It will increment RAX and then jump back here. That means now we will be at the first character. And it will get the first character from the buffer, first character from the key, and it will go on like that. Until all characters are done. And in that case, if it has never jumped out, it will go to label correct, as you can see here, because that, when it's 9, that means it's already looped 9 times, so 0 to 8. That means it's correct, and it will go to label correct. In label correct, it will say that, at this point it knows that all the bytes of your string are equal to the bytes of the key XOR 69, and it knows that the answer is correct. And it will print the message correct by moving it into RDI, called printf, and jump to after, so it skips the printing the wrong, otherwise it'll print both of them. And then it will call leave queue and red queue. And just as I call enter in the beginning, leave queue and red queue is basically the reverse of that. What if you take the 9th bit of BL? Is that the first bit of DH? Well, you cannot actually perform arithmetics on the registers itself, or the memory locations of the registers. You cannot just say, take the memory location of the register, go 9 further. So you can actually only do arithmetic with what is inside of the thing. And the 9th bit of BL with the mov B. Oh no, basically this first thing will always equate to a memory location, and we load the stuff that is in the memory location into BL, namely that character of the key, that character of the buffer. Yeah. So this basically creates a memory location, and that is what it uses. It will detect by itself. It basically has different instructions for move register to register, move memory to register, move register to memory. That are all different instructions, and that can all be. But the compiler takes care of that. All you need to know is just move and move B, move Q, etc. We can actually look at this program. So if I run compile and out, yeah, here it will say wrong. If I do gdb out, I can actually look at how the program functions. So if I say start again, and I run through the first few instructions, this one will print the string. We'll do that up here. Or, yeah, it already did that. And now we will call scanf, and I will enter a few correct things, but not everything is correct, and then a bunch of garbage. Now you will see it will call string length. And the string length of our string, namely is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, which is 0xb. And 0xb is loaded into RAX, as you can see here. It will then compare 0x9 to RAX, in this case 0xb. It will see that it's not equal, it will jump to fail, and it will print the incorrect text and quit the program by just doing the leave queue and red queue. Let's try that again. How about we enter something with a C, and then 8 A's. 1, 2, 3, 4, 5, 6, 7, 8. Now the yeah, I should probably first run through the code until it gets to the start. C 1, 2, 3, 4, 5, 6, 7, 8. I cannot count. 1, 2, 3, 4, 5, 6, 7, 8. Now it will call string length, and hopefully there should be a 0x9 in RAX. There we go, it is. Okay, so the next step, it will not go to G and E fail. So if it gets here, it means it's a length of 9, that's correct. And here we'll start a loop. So here we'll see, okay, compare 9 to RAX, Nope, it's not online yet, so we will continue. We will get the first byte from key and buffer into there. So here you can see the first byte of the key is loaded into, let's see, what was it again? BL, and the first byte of the... either one of the two, it doesn't matter at this point. Because XOR can be done with both of them. But here you can see that because all the rest of the register is 0, it will only show the last nibble, which is BL and CO in this case. So these are the two values that are used in the check. Then we call XOR BL 0x69, and as we can see in the wrong one, in the lab manual, XOR will say so we have the first, the second, and the source and the destination. Let's say destination is source XOR destination. So in this case, this is the code we get a look at. BL will be XORed with 69 and then put back into BL. So here you can see before it is 2A, and if I now press enter, it will be XORed with 69, which we know is 2A. It will compare if the two are the same, and then if they're not equal, it will jump to fail, but they're equal. So it will jump to the next one. It will increment RAX, so we know at which value we are, namely now we are 1, and it will jump back to loop. So here you can see it's started the loop again, it will compare RAX to 9, if not, it will go to label. Now it moves everything into the registers, XORs, and as you can see, these are not the same. 0x8 is not the same as 0x59, so it will go into fail, print the incorrect flag, and exit. Jelle asked, where are the flags stored? Good question. Somewhere in the CPU, there are the flags stored, namely the carry flag, 0 flag, sub flag, and I think there were a few other ones, but you don't really have to worry about this. Basically just know that the CPU itself stores them. They're basically just another pointer, but then with the flags, like the lecturer mentioned R flags. But you don't need to worry about that. All you need to know is that the compare influences the flags and that the jump looks at the flags that were influenced. Okay, so now if I look into my handy dandy answer that I gotten from somebody else, if we can look at how the code looks if I enter the correct password. So I will go through this, call printf, which will print the right thing, and you will see it here because it's not on a new line. So if it prints it up there, then it wouldn't make sense. But if we enter the right password, spoiler alert, this is the right password, we can see, okay, is the length 9? If not, it will jump to fail, but it doesn't, so it is 9. It will loop through this code 4 times, or 9 times, namely checking. It doesn't jump to fail, so we know that this one is correct. Okay, good, go to the next one. Move the bytes in, check if it is, if they're correct. If not jump to fail, they are. Go on, go on, go on. And it will keep incrementing RAX. It's currently at the 4th character. Okay, it's now at the 9th character. So here we'll see if RAX equal to 9. In this case, it is. Then it will jump to label correct. So we know it didn't break out at any point. It's a label correct. Move the correct string into RDI, which is, in this case, then the place where the correct string is loaded, namely 0x40116E. It will print that. It was printed above here, but you can't see that now anymore. And it will leave. And now it will do some other bullshit. But after you see main is done, and it starts saying shit about libc, you can know, okay, my program is done. So that is a run through of my self-made CTF program thingy. Let me go through one more thing real quick. I'm getting some questions about what Pwn debug is and what the program is I'm using. It is Pwn debug. So basically, if you Google Pwn debug, it's the very first link. And all you need to do is you can literally just copy paste these 3 lines into your thing. first you gotta have GDB installed. If you do not know that, the commando is sudo apt-get install GDB, and this commando basically means as administrator, package manager, please install the GDB, and GDB is just the debugger, but I am using a extended version of that, but that will require GDB. So here I can enter my password, and it will say, okay, it's already on the newest version, but for you it will install it. And then after that you can literally just copy paste these 3 lines, and I will send this in the chat real quick, into the thing. And also, if you cannot copy paste into the terminal, what you gotta do is you click into the terminal, right mouse here, edit, and then paste. That's the way you gotta copy paste. And if you do that, it will create a, oh yeah, very good note from Warkit to Sam. Basically, you gotta also do sudo apt-get install git, because it uses git to download the bone debug, and if you don't have git, it won't work. Okay, so we've gotten the GDB, we've gotten everything else down. Yeah, I see. So I think that should be it. I am now open to questions. If you have any questions, please unmute yourself.
Yeah, I've never worked with C either, so I'm kind of getting an issue with that. How to install it?
Wait, what did you say?
Like, I sent the problem in the CSC general.
In the CSC general?
Yeah. Okay.
Mic off.
Okay. Somebody else is asking a question there. I will keep on replying there. If there are any other questions, please let me know. Anybody?
What did you say about pasting in the thing about again?
So basically, if you want to paste something, you can go right-click on the top of your screen. It doesn't work. It doesn't work anywhere else. I think it can work, but not in all cases. Yeah, this is with Windows Subsystem for Linux.
Wait,
but
doesn't
if you want to be sure,
I sent it.
Doesn't Control Shift V work?
It can work, but it depends on your config.
I see.
Yes, it's asking Jurre, are you using 20.0.4? I am not using Ubuntu. I am using Kali Linux, which is basically Ubuntu but with other shit pre-installed. However, the newest version of Ubuntu is fine.
Oh, Jurre, I have another question. I heard that you said that we should use the lab manual to like learn and shit. But do you think would it be also a good idea to like look at tutorials and like do exercises based on like the other how do you call it?
Intel architecture?
Yeah, the architecture. Or should we just stick to this one?
I would say, especially when it comes to writing, do stick with this one, because otherwise you will get confused and it will mess it up.
Is it a big difference?
The only differences are the notation. I mean, like, we have source into dest and dest into source. Intel is dest into source. Out of source, I guess.
Yeah.
Let's see. There are some other differences, like in the AT&T syntax, you've got the MOV-Q, MOV-W, etc., which is like moving only a byte, 80 bytes, etc. You've got the syntax that all the registers need to be precedented with a dollar or a percentage sign. And all the other like values would need to be precedented with a dollar sign. That is not the case in Intel. This syntax with the move B is not the same in Intel. And I think that's just about it.
Alright, and what do you recommend for like the noobs and like people like me who haven't done any assembly before?
I've got a quick question from the chat. So Theo is asking, am I a TA? I am not. I might be next year, but this is my very first year that I'm just like you guys, I'm at the university for 3 days. I made this before we had an assembly lecture. It was hard. No, but yeah, I'm not a TA. I do not accept money. If you need help, just come to me. If I don't know, we'll go to a TA. but yeah, I just like helping people, and it will help me with like understanding stuff better if you guys help. And thank you for Basic for saying I'm doing a spectacular job. Yella said something in the chat saying debug symbols is -v. That is not correct. -v actually means verbose for the compiler. And let me show you the difference between compiling with and without. So this is what happens if you compile without the verbose flag, and this is what happens if you compile with the verbose flag. It adds a bunch of shit, but that's because compiling is actually a really fucking difficult subject, and they made this one command to make it a lot easier for us. However, a lot still happens under the hood, and sometimes you have to see what is actually going on and why it's not working. And this is excellent for that. Can you share the pulver code there? Yeah, sure I can. Let me actually move my entire assembly slash into mount. I'm not moving that, I'm copying that. Assembly into mount the desktop. Hello? Capital J maybe?
Mic on.
Oh, you.
Mic off.
So now I should have a assembly folder
Mic
on my... Don't talk shit about my Doofenshmirtz, my man. Shit's fire. Okay, so I've got an assembly folder here, and here are all the 3 files. Alright. If you guys make anything else for yourself that you are not going to be using, and this is very important, I stress again, that you are not going to be handing in as assignments, please do share them in the channel so others can learn from it as well. If you are using it for an assignment, do not share them anywhere. It will be fraud. Don't even let somebody look at your code. That shit's like, Andy will cry, like literally. Anyways, yeah, you can stop the recording. There is something that I